now talk about something called functional completeness. The idea is like this. You see, we have talked about so many different kinds of gates. Now, if I ask you a question that what kind of gates will be sufficient for designing a circuit? Do you need all the different kinds of gates, AND, OR, NOT, NAND, NOR, exclusive OR, exclusive NOT, everything? Or even if you have a small subset of gates, that will be sufficient to design everything or every circuit. This forms the notion of functional completeness or the universal set of gates. So, the title of this talk is functional completeness. Let us understand the notion. Now, in switching algebra, whatever we have seen from the basic definition, the operations defined are NOT, AND and OR. What does this mean? That any switching expression that you write is just a combination of AND, OR and NOT, nothing else. So, if I have sufficient number of AND, OR and NOT gates available with me, that should be enough to design any circuit I want. So, this set AND, OR, NOT is by definition functionally complete, because the definition of switching algebra says that with respect to the variables and the constants, these three basic operations are defined, AND, OR and NOT. So, if you have gates to perform these three basic operations, you can realize any switching expressions, because switching expressions are formed only using this AND, OR and NOT operators. Okay. So, the first thing we can say is that NOT, AND and OR, they are functionally complete. So, let us take a very simple example, say a switching expression f equal to a bar b and b c bar d bar. So, you see that it consists of only NOT, A is NOT, C is NOT, there are some AND and there is a OR. So, if I want to realize it is very simple, I need two AND gates, I need one OR gate, I connect them like this. First one is A bar B. So, A I connect using a NOT, becomes A bar, and B. Second is B C bar D. B comes directly, C comes through a NOT, C bar and D. This is the realization. I need only AND, OR and NOT. So, given any switching expression, we have nothing but AND, OR and NOT in it. So, this set AND, OR, NOT trivially is functionally complete. Such a set using which I can realize or implement any function is said to be functionally complete, right. So, with this notion, let us look at what other gates or set of gates they possess this property. But one thing we shall be assuming that this AND or NOT is our basic set. So, if I say that some other gate XYZ is also functionally complete, then we have to show that using XYZ I can implement AND, I can implement OR and I can also implement NOT. So, if I can show that, then only I can claim that XYZ is also functionally complete. Okay? Fine. So, we shall show some examples now. Okay. The first and most important claim, NAND gate. So, you know what a NAND gate is? NAND gate symbolically is shown like this. There are two inputs A, B and the output, let us say if it is F. So, F is nothing but the AND of the two, not of that. This is how NAND is defined. Now, what we claim is that NAND is functionally complete. What does this mean? That if I have only NAND gates, then I can build anything. So, my circuit can consist of NAND gates only, no other kind of gates are required. Okay. So, NAND is some kind of an universal gate, this is our claim. Let us see. So, as I said, the NAND function is given by NAND of A B is A and B not. Now, if I want to show that this is functionally complete, as I said, I will have to show that I can realize AND, OR and NOT using NAND. Let us see how this is possible. NOT, just remember this expression, NAND of two variable A B is just this A and B not. Let us say I take a NAND gate, there are two inputs, I tie the inputs together and I apply a variable A. So, what will be my output? It will be A and A bar, this is nothing but A bar, which means I can implement NOT. Then let us see AND. Well, if I have a NAND gate with inputs A and B, in the output suppose I connect a NOT gate, I already know how to build a NOT gate, I connect a NOT gate. So, this will be NAND, NOT of a NAND is nothing but AND. So, I get an AND gate. You see, just algebraically you can write like this AND is A B. So, you can do a double complementation A B bar of bar. Now, A B bar you can write A B bar and A B bar, same thing twice. So, this A B bar is implemented here, this is A B bar, and A B bar and A B bar, this is implemented with the second gate, this is basically not of that, this implements AND. So, you also have a AND. Well, OR is a slightly more complex structure. See, OR you can implement like this. First you need two NOT gates, you apply the two inputs here A and B. So, you have A bar and B bar implemented. Then you connect these two to another NAND gate. So, what I say is that this will implement OR. So, the proof is this, OR gate by deMorgans theorem you can write like this, A bar and B bar of bar. Now, this A bar is nothing but A and A bar, B bar is nothing but B and B bar. This A and A bar is implemented by this gate, B and B bar is implemented by this gate, and whole NAND is implemented by the third gate. So, you can also implement OR. So, this shows you that NAND gate is functionally complete and any kind of function switching expression can be realized using NAND gates alone, because we have already proved you can design a NOT gate, AND gate and OR gate using NAND only. Okay. So, continuing with the discussion, NOR is also functionally complete, just like NAND, the NOR gate is also functionally complete. So, if you have only NOR gates, then also you can design and implement any kind of circuit. So, in a similar way to NAND, let us also try to prove that NOR gate is functionally complete. Let us see. So, the first thing is that the NOR function is nothing but this A or B, not of that. Now, realization of basic gates, well, in a manner similar to NAND I am showing here, and the corresponding circuits I am showing one by one. First, NOT, you take a NOR gate, tie the two inputs together just like a NAND. If we apply A, it will be A or A bar, just this. This A or A means only A. So, the output will be A bar. So, NOT can be implemented. First look at OR, because OR is easier. You take a NOR gate, you apply A and B. So, what you get here? You get NOR of that, A plus B bar. Now, you connect a NOT. NOT you already know how to do a NOT. So, you will be getting finally OR A plus B. So, OR can be implemented. Now, AND structure is again similar to OR for an AND. So, what you do? You start with two NOT gates with the two inputs connected together, A and B. So, here you have A bar, here you have B bar. Then you connect them together using another NOR gate. You will be getting A and B. The proof again goes like there. From A B by deMorgans law you can write like this, A bar or B bar, and this A bar you can write A or A bar, B bar you can write B or B bar. This A bar you are implementing by this gate, B bar you are implementing by this gate, then finally you are taking NOR of A bar and B bar, third gate, right. So, in a manner similar to a NAND, we have also shown NOR is also functionally complete. So, if you are given only NOR gate, we can implement any circuit that we want to. Let us look at some other functionally complete sets also. Well, this is quite simple to justify. I am saying that this set, suppose I do not have OR gates, only AND and NOT. I am saying this is also functionally complete. Well, what is my justification? I have AND gate, I have NOT gate. Okay. Now, if I connect them together, what gate do I get? This is equivalent to a NAND gate. Now here we have already proved that NAND gate is functionally complete. Now, because I can implement a NAND gate using AND and NOT, so this will also be a functionally complete, AND NOT is also functionally complete. Okay? Simple to say, because we have already proved NAND is functionally complete, and using AND and NOT I can build an AND, right. So, the justification is very simple. Okay. So, in a similar way you can also say that OR and NOT is functionally complete, because you have an OR gate, you have a NOT gate, connect them together, you get a NOR gate. Now, NOR gate is functionally complete, this we have already proved. So, if I have only OR and NOT, so we can build a NOR using that, which is known to be functionally complete. So, this will also be functionally complete. So, we have seen, means other than AND or NOT, 4 sets of gates. One is NAND only, NOR only, AND NOT, OR NOT. Okay. Now, these gates are functionally complete, means without any external, means other kinds of inputs, because you can realize any function just by using these gates. So, what I mean here is I will be explaining that with the next example. Here what we are saying is there is another set we are talking about. We are talking about AND XOR. Well, XOR gate you already know what an XOR gate is. An XOR gate symbolically is shown like this. The two inputs are A B, if the output is F. Well, sometimes the XOR is expressed symbolically written like this, A XOR B, is written as A bar B or A B bar, because the definition of XOR I gave earlier is XOR will be 1 if odd number of inputs are 1. Odd number means with respect to A B, if A is 0, B is 1 or A is 1, B is 0. Odd means one single one, that is odd. So, A bar B, A B bar, right. Now, here what we are saying that only AND XOR is not sufficient, we also need the constant value 1. Why? The reason is very simple. Suppose I have an XOR gate. XOR function already I have shown. What is XOR function? Let us say to the first input I apply A, to the second input I apply a constant 1. So, what will be my output? Just follow this rule, A bar B, B is here 1, or A B bar, B bar will be 0, bar of 1. So, second term will become 0, only the first term will remain, which is A bar, which means an exclusive OR gate with one of its input as 1 is equivalent to a NOT gate. So, I can build a NOT gate using an exclusive OR gate and the constant 1, and I already have AND gate, and we have already shown that AND and NOT are functionally complete. So, I have AND and I also have seen how to build a NOT. So, this will also be functionally complete, right. So, the justification is fairly straightforward. This is exactly what is said, that you can implement a NOT by setting the second input to 1, and we already have shown earlier NOT and AND is functionally complete. Similarly, instead of AND you can go for OR. The logic is similar. So, I am not going into detail, because NOT we have seen exclusive OR with a 1 you can implement a NOT, and this OR gate is already there. OR and NOT we have already shown earlier, this is already functionally complete. Therefore, OR XOR 1 will also be a functionally complete set. Okay? So, these are the things you have to remember. So, if you are designing any circuit and someone gives you some gates to design, you can check whether those gates are sufficient in terms of functional completeness. If they are functional complete, then you know that well I can design any function using those gates only. Okay. All right. Let us now look at a slightly different kind of a functional block, not exactly a gate. Well, we had talked about a multiplexer earlier. So, we considered a 2-line to 1-line multiplexer. So, how does a 2-line to 1-line multiplexer look like? It is a blocks where there are two inputs A and B. There is a select input S and there is an output, let us say F. This is how a multiplexer look like. So, how does it work? If the select input is 0, then the output will be equal to A. The first input will be copied to the output. But if S equal to 1, then the second input will be copied. So, it is like a controlled switch. Depending on what I apply to S, either A is switched or B is switched. Okay? Let us see that whether this is functional. Here what means, we have mentioned another thing, that I need both constant 0 and constant 1 to make it functionally complete. So, talking about the function, just you see I can directly write down this expression. The output function of a multiplexer is A S bar B plus S. What is the meaning? You see, if S is 0, output is A. S is 0 means S bar and A, S bar and A. S is 1 means S and B, S and B. You can directly write an expression like this. Okay? This is what a multiplexer is. Now, realization of the other gates can be followed like this. Just look at these scenarios. First, NOT. Let us try to build a NOT. So, what we are saying that the first two inputs I apply 1 and 0, like in this multiplexer I apply a 1 here, I apply a 0 here, let us say, and to the select line, third one is the select line I apply the variable A. So, if I substitute 1, 0 and A in this expression, it becomes A, that means 1 A bar plus B, B is the second one, 0 A. If you simplify this, this is only A bar, which means I can implement NOT, but I require a constant 1 and also a constant 0. I can also implement an AND. How? I can apply this input A in the first one, 0 in the second one, and I already know how to implement a NOT. So, suppose the other input I do a NOT and I apply B bar to the select line, A 0 and B bar. Then if I just substitute the values in this expression, A bar of this becomes B plus second one 0. So, this will become 0 and A B. I have implement AND. So, I can implement a NOT and an AND, and you already have seen earlier that NOT and AND are functionally complete. Therefore, this 2 to 1 multiplexer is also functionally complete, provided you have the constants 0 and 1 available with us, right. Okay. Now, let us look at some interesting observations. So, when you design a circuit, sometimes we need to transform a circuit from one form to another, change the kind of gates that you have. So, let us look at some of the very common transformations that we carry out. First observation that we make is very important. It says that a 2-level AND OR circuit is equivalent to a 2-level NAND circuit. So, what I mean is that if I have a 2-level circuit AND OR like this, this observation says this will be equivalent to keep the circuit structure the same, just replace all the gates by NAND. So, function will remain the same. You keep the inputs A, B, C, D as same. Here also it will be A, B, C, D. Suppose the function was f here, the same function will remain f here. Now, the proof comes from deMorgans law. Just to see, if I have this A, B or see this function f, this realizes what? A, B or C, D. Now, I can do a double complementation, complement of complement in 2 steps, let us say. So, the inner one I can apply deMorgans law, something or something bar. What does this mean? This something will be not, plus will become AND, this something will become not, and then whole thing I have bar. See, A B bar is nothing but NAND of A B, C D bar is nothing but AND of C D, and something and something bar is nothing but NAND of that something and something. So, straight away these two are equivalent. So, if I have a 2-level AND OR circuit, just blindly I can replace all the gates by NAND gates, not necessarily 2 gates, any number of gates can be there in the first level, okay? Because deMorgans law can be extended to any number of inputs, right. This is one very important observation you should remember, and a similar observation exists for OR AND circuit. 2 level OR AND circuit is equivalent to NOR NOR. So, here also the idea is very similar. I have a 2 level OR AND circuit like this. So, here also let us say the inputs are A, B, C, D. What I say, this is equivalent to a similar circuit where all the gates are made NOR. So, again this follows from deMorgan's law, because if you say the function output is f, so what is f? F will be A or B and C or D. So, if you do it double complementation, again a complementation, then the inner one something and something bar, what will be that? Something bar or this something bar whole of bar. So, this means this A plus B bar means this NOR, C plus D bar means this NOR, and whole thing means this NOR. So, similarly 2 level OR AND you can directly replace by 2 level circuit with all NOR gates, right. This is very simple. Now, in general, if you have in any circuit, not necessarily 2 level, means it can be a multi-level circuit. I mean, if you apply deMorgan's law in a suitable way, and also if you use some basic transformation rules, then you can convert any multi-level circuit consisting of AND, OR and NOT gates using NAND gates only. Well, I shall be illustrating with some examples. Well, similarly we can do it for NOR gates only, but I am not giving those examples, you can try them out yourselves. But what examples I will be giving is, given any arbitrary circuit, I can convert them into NAND gates. It can be multi-level, not necessarily 2 level, but some basic rules are being followed here. Let us say if I have an OR gate with NOT gates in the input. Well, sometimes symbolically we write it like this, we show it as small bubbles in the input, bubble means NOT, okay. These are same thing. So, if you see what this functionally means, A B means this will be A bar B bar and OR of that A bar or B bar. So, what is A bar or B bar? According to deMorgan's law, it is nothing but A B bar, which means this is NAND. So, any OR gate with NOT gates in the input is equivalent to a NAND. This you should remember. This is nothing but NAND. In some book you will find NAND gates are shown like this, because they are equivalent, right. Let us now take some examples to show that how this kind of transformations can be carried out. Just a second. Yeah. Let us take a simple example. Let us say I have a circuit like this. So, I want to convert it into a pure NAND circuit. It is a multi-level circuit. Say there is an AND OR and also there is another AND. Let us say circuit is like this. So, what are the steps? The first step is that if we look at this part of the circuit separately, this part of the circuit. This is like a 2-level circuit AND OR, and 2-level circuit you already know that we can convert it into NAND blindly, because we have already shown that these are equivalent. Then lastly, we have an AND gate here. Now, what is an AND gate? We can write it like this. These are already in NAND, we have got in NAND, and this AND gate you can implement using a NAND gate followed by a NOT gate. So, you know how to implement a NOT using NAND. So, you see you have obtained a all NAND implementation of the original circuit, right, simple. Let us look at another example which will involve some OR operations also. Suppose I have a circuit like this with a NOT gate here, this goes to an AND, there is an OR gate here, output of the OR goes here, there is another OR gate and there is a NOT. Let us take a circuit like this. So, step by step let us go through the transformation. First is, if you look at these two gates AND followed by NOT, this is straightforward, it hits a NAND. You replace it by a NAND, and you have an OR gate here. Now, you already know how to implement an OR gate using NAND gates, follow that rule. You have a NOT, another NOT, you have a NAND. This is NOR, this NOR gate, and both of these will be going to the input of this AND gate, this AND gate. And then you have the final OR gate and the other input coming through a NOT. Okay. So, the first two part you have taken care of, converted them to all NANDs. Now, let us look at the rest. This is an AND gate. So, what you can do? I am just showing the equivalent circuit here. This circuit is already there. I am also drawing this part. This part is there, and they are going to the input of this AND gate. Okay. Now, what I am saying is that let us make this a NAND gate followed by a NOT gate. Let us say a NOT gate. This is equivalent to AND, and on the other input also I have a NOT gate which goes to an OR gate. Now, we have already shown that a NOR gate with the inputs NOT is equivalent to a NAND gate. So, finally, you have a circuit where you have this NAND gate, this two NOT gates using NAND, another NAND, they are connected to another NAND, and finally, they are going to the last NAND where the other input is straight away coming here. So, these two circuits are equivalent. So, you see, just by knowing some of the rules that you have already know and this kind of transformations that I just talked about some time back, you can convert any arbitrary circuit using systematic methods using NAND gates only. Similarly, you can do it for NOR gates also, the rules are pretty similar. So, with this we come to the end of this lecture. Now, in our next lectures, we shall be looking at some systematic ways of minimizing functions. So far, we talked about algebraic methods, and just by applying rules, by using ad hoc methods, we have tried to minimize. Means, as I said, if you remember the rules correctly, it will be easier for you, but if you do not remember the rules, you may not be able to minimize in an effective way. So, we shall next look at some of the more systematic ways to minimize and analyze switching functions. Thank you.